Okay, so while others are connecting, uh, we let me quickly revise what we did. We have finished naive-based classifier now, and I guess in last laboratory we have implemented this also. We have implemented both versions of naive-based, multinomial and Gaussian, isn't it? So we'll move to the next topic, which is Bayesian network. So before that, I can take one or two questions. If you have any doubts on naive-based classifier, or if you want to share anything related to naive-based classifier, you can post message here. We will first talk about that, and then we'll move to the next topic. So, do you want to ask any questions? Are there any questions? Okay, so let's move to the next part. If there are no other questions, we'll share my screen. So we talked about naive-based classifier. Let's try to look at it a bit differently. So I have drawn a graph here. The graph is known as dependence graph, which describes n variables x1 to xn and a class level y. So we can say this is a dependency graph of n plus 1 variable, where x1 to xn are attributes and y is class label. So every circle in this graph is a random variable, and arrow between the circles shows dependency between the random variables. For example, an arrow from y to x1 shows that x1 is dependent on y. Similarly, arrow from y to x2 shows that x2 is dependent on y. Okay? So this is what we have been doing in naive. So we didn't draw a graph formally, but if you see the probability distribution of naive, joint probability calculation of naive, it can be done by this formula. Joint probability of x1 to xn comma y is defined as or is equal to probability of x1 given y, x2 given y, up to probability of xn given y multiplied by probability of y. Right? This is what we have done. So this was our naive assumption. We said that x1 and x2 or the attributes are independent of each other and they come from identical distribution. So we call this IID assumption, independent and identical distributed. And we said that it depends only on class label. So we could simplify this joint probability calculation with this formula using the naive assumption. Now we will talk about a more general scenario where this naive assumption doesn't hold. And you might have also, while working with naive also, you might have realized that this is a pretty weak assumption. So it works for many problems. And many problems can be solved or modeled using naive-based classifier. But we know that in real world, attributes are often dependent on each other. So such assumption may not hold. In that case, we need to do something more than that. So we will talk about more general cases of such network, this dependency graph, where circle is random variable, arrow is dependency. We can draw much more complex structure from this dependency graph also, where we can capture dependency between the more complex dependency between the variables. Right? So this is what we will talk from now on. But is this clear, this dependency graph and the joint probability calculation? Any questions on this? One thing you might realize is that this dependency graph is a convenient way to describe the complex mathematical formula. Instead of writing this joint probability, I could draw this simple graph, right? And visually it is easier to understand. So that is also why people follow this kind of graph. And we will see in probabilistic graphical model plate diagram. This kind of diagrams are known as plate diagram, are very popular, where random variable its dependency and its combinations are implemented through such kind of figures. Yeah, so let's see what can be more general way of capturing dependency. For example, I can draw something like this. Now I have now this does not hold now the naive assumption does not hold anymore, right? Because here this variable x3 depends upon two variables x1 and x2. X1 in turn depends on y and x2 also depends on y, and y does not depend on anything. So what would be the formula of this joint distribution? Now if I want to write joint distribution of this, that is probability of x1 comma x2 comma x3 comma y. How do I calculate this joint probability now for this graph? So if I want to calculate probability of x1, x2, x3 comma y for the graphical model given above in the figure, it would be something like this. The joint probability of x1, x2, x3, y is equal to probability of x3 given x1, x2 into probability of x1 given y, probability of x2 given y, and probability of y. Right? Are you with me on this? Without any assumption, joint distribution is very difficult. If you do not assume any kind of dependency, then to calculate joint distribution of four variables, you need to try all combinations, like probability of x1 given everything else into probability of x2 given everything else, and so on. But here, since you are making this assumption, your probability calculation is little bit easier. On the same, and you also realize that now this is not in the framework of naive assumption that attributes are independent of each other. Now we have x3 dependent on x1 and x2. So this kind of dependency is possible. So the difference between the attribute and class label also doesn't matter much now. Now we say that this network has four random variables and their dependency is as shown in the graph. And since we are assuming this kind of dependency, the joint distribution can be given as per the formula that probability of x1, x2, x3, comma y is equal to probability of x3 given x1, x2 into probability of x1 given y into probability of x2 given y into probability of y. This could have been anything else also, but this is just one graph that we have assumed. So this is one part of Bayesian network where you draw a dependency graph of random variables. Now this graph can be manually constructed or this graph can be learned from the data also. So learning graph from the data is a more advanced concept and it is not, we will not cover it in our discussion. So for our discussion, we say that this graph is manually constructed. So a machine learning engineer would model the dependency between the random variables. And this modeling of dependency of random variable is completely a manual process that machine learning engineer would do. In case of naive, again to compare with naive-based classifier, in case of naive-based classifier, the dependency model was fixed. Since we have assumed independence between the variables, the dependency graph was fixed. Now the dependency graph is as per the design given by a machine learning engineer. And based on the dependency graph that you create, the model parameter would vary. So which are the model parameters in this graph? The model parameters are as shown here, right? The py, probability of y, probability of x1 given y, probability of x2 given y. All these are model parameters. x1y, y, x2 given y, x3 given x1, x2. These four are model parameters. And similar to naive classifier, we need to learn this model parameter in terms of conditional probability table, CPT. So for this figure, we need four tables. One for probability of y, one for probability of x1 given y, one for probability of x2 given y, and one for probability of x3 given x1, x2. Right? So, and how do we learn this conditional probability table? Who will answer this? How do we fill in this table? Where do we get this value of values from? Yes, as Keval is saying, we get this value from data. We look at the data, we again count the numbers as we did in naive classifier, and we fill in this table. Then we make use of this table to answer inference question. So the process remains same, learning conditional probability table from the data. Once the conditional probabilities are learned, use those probability values to answer inference question. Only one addition is that your structure is also now, your structure can also be different. That is the dependency graph. You can draw different kind of dependency graph to depict relation between random variables. So for Bayesian network, the learning part involves two things. So that there are two parts, learning part and inference part. Learning part involves two things. One is learning dependency graph. Here we are assuming that it will be done manually. So we will not go into learning of graph. Second is learning of conditional probability table, that is CPT. That we do from data, similar to what we did so far in case of naive classifier. So we learn from conditional probability table from the data. And then once that data for conditional probabilities are learned, next thing is use it for answering user query or inference question. So calculate probability of an outcome using Bayes rule. We apply Bayes rule for that. I will wait here for a minute. Please ask me if you have any questions. Is the structure clear? Is there any question on this? We have not done much so far, but is the direction clear? Is it clear? Where are we heading with this? What we are doing is now we are just dropping the naive assumption so that the graph can be anything. If I want to put everything in one line, then this is what we have talked so far. Okay, so let's take an example. Let us say these conditional probability tables are learn. We have from data we have already calculated this because this process I will not repeat. It is the same thing which we did in naive classifier also. Look at the data and see how many time y is 0, how many time y is 1, how many time x1 is 0 given y is 0 and so on. So we have been through that, so I will not repeat that. So note down these values. This will be used for remaining of the lecture. So if you are on mobile or device, if you want to take screenshot, take a screenshot. If you want to note down, then please note down this value. We will use it for our calculation. So after training, a Bayesian belief network would look something like this. Okay, no, this is not necessary for now. After training, a Bayesian network would have random variables, dependencies, and conditional probability tables or model parameters. Once this is done, your network is trained, and now you can use this network to answer inference question. Have you noted this down? Okay, so if you have noted this down, let's try to answer the inference question. So now the question can be something like this. What is the probability of x3 equal to 0 given x1 equal to 0, x2 equal to 0, and y equal to 0? How do we answer this question? So we apply the rule of joint probability, and the formula is something like this. So probability of x3 equal to 0. So which formula, which rule of joint probability I am talking about here? I am talking about, let me write here. I am talking about probability of A given B is equal to probability of A and B divided by probability of B. Similarly, for more than two variables, if I am writing probability of A given B comma C, it will be probability of A, B, C divided by probability of C. So probability of observing A given that B and C are observed is equal to probability of observing all three A, B and C together divided by probability of observing B and C. How many times you have seen B and C? And out of those total occurrences of B and C, how many times A has also occurred? So that is joint probability of A, B, C. We have done this a number of times by now. So this should not be very difficult to understand. So this blue equation, we have used this equation to calculate this probability of x3 given x1 equal to 1, x2 equal to 1, x2 equal to 0, and y equal to 0. So that is joint probability of x1, x2, x3, y divided by x1, x2, y. Please stop and ask me if you still have any questions or any doubts related to this, because this is the pivot point, or this is at the heart of all computations of Bayesian networks and naive classifiers. So is this clear how what we are doing here? Okay, good. So now, how to model this joint distribution? The numerator part we know now. Numerator part is joint probability of x1, x2, x3, and y. Okay, Keval is writing something else. No, so this what you have written, Keval, here holds for naive-based classifiers. If we believe that the classifier we have used is naive-based, then your formula is correct, right? But now we have moved on. Now we are saying that this is not naive-based assumption. This is not based on naive assumption, but this joint probability of x1, x2, x3, x4 is rather defined by, let me write again here, so that would be better. Probability of x1, x2, x3, and y is equal to probability of x3 given x1, x2 into probability of x1 given y into probability of x2 given y into probability of y. So now this is our model. Right now our model is defined by this. So if I want to calculate joint distribution of x1, x2, x3, and y, I need to use this formula. So how do I calculate numerator? The numerator, before that, how do I calculate denominator? What is the problem? So the joint distribution is defined for four variables x1, x2, x3, and y. In denominator, we are missing x3. So before we could calculate, before we could apply this formula, we need to introduce x3 in our joint distribution of denominator. But x3 doesn't matter in denominator. So what we do is, who will answer this? The same old technique which we have applied in naive classifier also. Since we cannot talk about x1, x2, and y without x3, we need to introduce it. But x3 doesn't matter. So what we do is we marginalize over x3 and it becomes something like this. Right? What we do in marginalization is the variable which is not observed, for that we will add all possible outcome of that variable and sum over it. Right? So now we have three probability distributions, or three probability of distributions x1, x2, x3, and x4. x1, x2, x3, and y. Two are repeating. If you notice, in numerator also we have x1, x2, x3, y0, and x1 equal to 1, x2 equal to 0, x3 equal to 0, y0, and x1 equal to 1, x2 equal to 0, x3 equal to 0, and y0. So these two values we need to calculate. So can anyone quickly calculate and tell me the answer? or you want me to go through one more step of the calculation? So what we do after this is it will be like this. Joint probability of x1, x2, x1 equal to 1, x2 equal to 1, x3 equal to 0 and y equal to 0 is equal to probability of x3 equal to 0 given x1 equal to 1 and x2 equal to 0 multiplied by probability of x1 equal to 1 given y equal to 0 multiplied by probability of x2 equal to 0 given y equal to 0 multiplied by probability of y. Isn't it? Similarly, for the denominator, again you can put this value. Look at this formula, think over it for 1 or 2 minutes. I will wait and please ask me if you have any questions on this. Is this clear? Any questions? Okay. So now how do we calculate this? From where do we get this value? We can, yes, from CPT. I guess you mean CPT. We look at the conditional probability table and we fill in this value. So let us do that. I have final answer, but I will erase it for now. So now we look at the conditional probability table and we try to fill in this value. So probability of x3 equal to 0 given x1 equal to 1 and x2 equal to 0 is 0.4. Right? Or did I make a mistake? Let's see. Okay, 0.4, yes. Into probability of x1 equal to 1 given y equal to 0 is 0.8 into probability x2 equal to 0 given y equal to 0 is 0.4 into probability of y equal to 0 is 0.3. Divided by the same thing repeats first. And plus what? Probability of x3 equal to 1 given that x1, x2 are 1, 0. That is 0.6. Into probability of x1 equal to 1 given y equal to 0. That is 0.8. I think everything else remains same, right? And so all these are common terms. So rather than doing the multiplication, I would do it like this. So it will be 0.4 divided by 0.4 plus 0.6 is equal to 0.4. So Keval says that Kaushal says it is 0.4, and I also get the 0.4. So are you all getting the same answer? 0.4? Okay. So I think it is 0.4. And if you notice that we have this value in our conditional probability table also. This x3 equal to 0, given x1 equal to 1 and x2 equal to 0 is marked here as 0.4. But I wanted you to go through this calculation to realize that everything adds up and you get the right answer. Right? Just look at it properly and tell me if you have any doubts or any question on this. Okay. So I guess it is clear. So the first example was simple because the question, the inference question which I have asked was directly from the conditional probability table. That what is x3 equal to 0 given x1 equal to 1 and x2 equal to 0. So that dependency is directly there in the CPP. So you got the answer. But in Bayesian network, unlike a naive-based classifier, you can ask question about any random variable. The inference question can be about any random variable, and we will see that using these formulas which we have discussed so far, we can answer any inference question on these four random variables on which the network is modeled. For example, if we are asked question like this, what is probability of y equal to 1 given x3 equal to 1? Then we can answer this question also. So now my inference question, the probability that I am asking for is not directly there in my conditional probability table. You see, conditional probability table does not describe this probability. It describes only this probability. So can I answer this question? Yes, I can. I can answer this question, and we will see how. The tools and techniques remain same. We will use the same technique and same formula, and we will apply same Bayesian rule here. So again, probability of y equal to 1 given x3 equal to 0 is Yes, as Keval is saying, is probability of y equal to 1, comma x3 equal to 1 divided by probability of x3. But now, what next? Your joint distribution again is defined over four variables, and in your numerator you have only two variables. X1 and x2 are missing. So what would you do in this case? You marginalize over x2 and x3 in the numerator part, and in denominator part you will marginalize over x1, x2, and y. So it will be something like this. Now I'm introducing sigma notation to make it less cumbersome. Otherwise, I need to write four formula in the numerator and eight formula in the denominator. Instead of that, I'm introducing this sigma. But that doesn't mean that you do not need to calculate. You have to calculate. So you need to do the tough job. Let us see what answer we get. Try to calculate this and give me the answer. Yes, sir. You have four terms in the numerator and eight terms in the denominator. So please calculate this term and give me the answer and ask me if you have any questions in between. I will also do bit of calculation along with you. So let me list out the terms in numerator. This is numerator part, right? And denominator, everything in the numerator plus situation where y was 0. So denominator would be this is denominator part, right? So four values in numerator, eight values in denominator. Can you quickly simplify and calculate these answers? Okay, so tell me these values. Let us do this. Probability of y equal to 1, x3 1, x1 0, x2 0 is probability of, right? Okay, Kaushal says 0.175, but with maybe. So why Kaushal it is maybe? Earlier also your answer was maybe. So if you done exact calculation, then it still be 0.175. But anyway, let's wait for this. Frequency numerator is 0.455. I'm doing some computations for everyone to understand if you are still finding it difficult. So x3 equal to 1 given x1 and x2 0 was 0.8 multiplied by x1 equal to 0 given y equal to 1, that is 0.6 multiplied by x2 equal to 0 given y equal to 1, that was x2 equal to 0 given y equal to 1 was 0.3 multiplied by y equal to 1. That is 0.7. So tell me if I'm making any mistakes here. And this turns out to be for 0.8 into 0.6 plus 0.3 into 0.7. Let me send out the calculator. Point 1. Okay, 0.1008. Okay. So I have found out this value as 0.1008. Can you help me writing all other values? What will be the second value? The value here? Okay, 0.205. Okay, good. What about third value? Here? 0.0504. This is case, okay. Fourth value? 0.098. Okay. So I will repeat this four value here also in denominator, and then you tell me the remaining of the value. Now what about this value? Can anyone calculate and answer this value? Probability of y equal to 0, comma x3 equal to 1, comma x1 equal to 0, comma x2 equal to 0. What will be the answer here? Okay, Rikin is calculating. Has anyone finished calculation? Okay, well, I think 0.0192. Okay. Then the next one, 0.0252. Okay. Then the next one, you will say 0.0576. Okay. Then 0.072. So these are the values we found. And we get A is equal to 0.1008 plus 0.2058 plus 0.0504 plus 0.098. And in B we get all of the above plus other terms. Right? And that sums up to, what is sum of A? A is 0.5455 and B is 0.629. And the final answer is probability of y is equal to 1 by x is equal to 1 is 0.455 divided by 0.629. That is 0.723. So yes, if x3 is observed to be 1, then we believe that y would also be 1. Okay, Kaushal is saying that I am getting final answer greater than 0.7. Maybe not correct because each time I am calculating by take common and pencil, and I simplify this formula to so it might be possible that I will make mistake during simplification. But I think Kaushal, we are also getting 0.7234. So Keval, Rikin, Kaushal, I think we are all on same page, isn't it? Okay. So what does it mean is, so it means that whenever you see x3 to be 1, chances of y to be 1 is also very high. This is what we understand from this computation. So one purpose of this discussion is to make you understand how do we compute this probability. Another 2 points on side note with which we'll end the session is, so one is that if you notice now inference question can be anything. Like I have asked y is equal to 1 given x3 equal to 1. If you know, look at this diagram, you might feel that y is not dependent on x3. Then why am I asking this question? But this is my model, and these are the model parameters. The inference question can be anything. So you can look at it like this. So I have observed x3 to be 1, and I become curious like if x3 is 1, what will be the value of y? So that's why I asked this question that y equal to 1 given x3 equal to 1. And the model parameters which I have are sufficient to calculate and answer this query. So the query can be anything in this Bayesian network. So unlike naive-based classifier, where we only predict class label given the feature, Bayesian network is a more general setup where you can query about any random variable given the observation of any other random variable. And the network is capable enough to get the answer, right? So that is one part. Second part is you might have noticed that the calculation is very cumbersome. It takes a lot of time to calculate this value. So can anyone tell me how much time in worst case this calculation can take? Here we had four formula to compute in numerator and 8 in the denominator, right? Why 8 in the denominator? Because we marginalize over three variables. So if your Bayesian network is of n variables, in worst case, you might need to do marginalization over n minus 1 variable. So the computations you might be end up doing is, as Keval is saying, 2 raised to n. So the worst case complexity of this kind of computation is 2 raised to n, and we know that 2 raised to n is something that we do not like. It is not polynomial, it is exponential time, and we want to improve over that. So exact inferencing in Bayesian network is, as Keval is saying, a hard problem, and there is no polynomial time solution for that. So we will try to do approximate inferencing on this. So in later lectures, we'll talk about approximate inferencing in Bayesian network. But for now, this is how the inferencing is done in Bayesian network. We will end the talk here. Uh, Please go through this, and if you have any questions, we will take the questions next time.